So I will talk a little bit about high temperature shaped memory alloys. Before I will start, I would like to acknowledge my co-workers. Actually, this was a collaboration between the group at the University of Kassel and my group in Hanover. So why are high temperature shaped memory alloys interesting? Actually, there's lots of application. This here is the famous variable geometry chevron from Boeing. And here you see a spring that can be used to adjust the clearance gap, say, in a gas turbine. And this will save you a lot of energy. So there are many more conceivable applications like these in energy conservation, transportation, or robotics. So people really have interest in high temperature shaped memory. The problem here is that standard nickel titanium doesn't work because it has phase transformation temperatures below 100 degrees C, which means that the surface temperatures are also below 100 degrees C. One way to solve this problem is you take nickel titanium and then you add, say, platinum, palladium, or gold. The problem here is you need around 30% of these node elements, which clearly drives up the cost quite a lot. You can avoid these elements by, say, adding hafnium, but then it becomes difficult to process the material. So if you're really interested in, say, mass applications, what we need is a temperature beyond 120 degrees C, something like 3% strain, fairly cheap materials, and that's it. We try to address this within a so-called research unit sponsored by the German Research Foundation, where we try to push up the temperatures of the phase transformation. Today, I will only talk about one issue about cyclic stability of these materials, because this is a key issue. Okay, so for high temperature actuation, we choose titanium tantalum with some ternary elements like aluminum. And it's well known that this material does show a one-way and a two-way shape memory effect beyond 120 degrees C. It is fairly good to work. Basically, it's titanium. And the constituents in there are reasonably priced, I would say. So this looks like a good material. And it's also all the crystallography is known. We have an austenite called the beta phase, which is a BDC structure. And we have the martensite or alpha double prime phase, which is orthorhombic. And all the crystallography is known, so we just can take the material and get started. So we started with so-called load increase tests. Here you see the strain on the material. This is the temperature. And then we heat up the sample from room temperature to above 400 degrees C, cool it back to force. If you do not apply a stress, you don't see much, right? But if you do apply a stress, then certain martensite variants are favored, and then suddenly you see a transformation strain. And as you increase this stress, then you get more and more strain, and in the end you get around 1 or 1.5% strain. And the good news is here the temperature where this phenomenon happens is around 200 to 300 degrees C. So it looks like an interesting material. The problem is shown up here. If you go to 200 MPa, then the loops do not close anymore, and you have some residual strain there. In the next step, we did some digital image correlation in these experiments in situ. What you see here is the strain field upon unloading for 50 MPa. So there's basically no strain, but for the high stresses, you see there are these islands popping up with fairly large strains locally of the order of 3% or so, which means there's a lot of plasticity going on. So for all the following experiments, we limited ourselves to 100 MPa, which is in between here, so to avoid this problem. Okay? So next thing is, again, strain versus temperature. This is the titanium tantalum 30. In every case, it was 100 megapascal bias stress. And then when we cycle, we see this nice hysteresis there with a strain approximately 1%, looks good. However, in the second cycle, the material already starts to change its behavior. In the third cycle, it's more or less gone. After 4 cycles, it's totally gone. So clearly, nobody wants to have an actuator that can only operate for 4 cycles or so. Right? So we have rapid functional in this material. That's not really useful. The data that you see here was actually from a slow test. We changed the temperature by only 0.33 degrees C. So this is the data that we have just seen. Then we repeated this test at a much faster rate. This is roughly a factor of 100. And this is the data that we got here. Looks pretty much the same, but in the slow test, it takes about 3 or 4 cycles before the material is gone, and now it takes around 300 cycles before you lose the effect. So this tells you it's not the number of cycles that's the problem, it's actually the time. So it's a diffusion control problem. So basically the material degrades because it's kept in this temperature range here for a certain time. So what's the reason behind that? We did some X-ray on this material. This here is the initial material. If you do X-ray, you get all those nice peaks. So it's fully martensitic. And then if you do an aging, this here is at 350 degrees C, you don't even have to cycle it. If you do X-ray after this aging, all the martensite is gone. It's fully austenitic then. And the reason why it's fully austenitic is because you form the omega phase, which is shown up here. The omega phase is really hard to see in X-ray. You see this tiny little extra peak. This is what stabilizes the austenite and what kills your material. The omega phase is much, much easier to see if you do TM. These are TM images. Here, these background speckles, that's the omega phase. And if you do selected area diffraction, you get these extra peaks in here. And if you pick one of those reflections and you do a dark field image, then you can see the omega phase, which is these tiny bright particles here. So the omega phase has a size of around 1 nanometer or so. And it's the omega phase that stabilizes the austenite, which basically degrades your material. So you need to do something about the omega phase. This here is electrical resistivity data. It's normalized by the electrical resistivity at 300 degrees C. And if you take this titanium tantalum alloy, you see that upon aging, the resistivity quickly changes. And if you do change your composition with some aluminum, you see that this degradation process is delayed quite a bit. So aluminum additions do delay this microstructural change. This doesn't only work for the resistivity, it only works for the cycling. So this is a modified alloy launch, titanium 30 tantalum with 3% aluminum. Again, a fairly slow test. Remember, this was the test where the material lost its properties after 3 cycles. Now with the aluminum, you see, is the first cycle. The cycle number 8 looks pretty much the same. And it takes around 30 cycles so before the material starts to degrade. So aluminum does help. It delays the formation of the omega phase, but obviously it doesn't really solve the problem. And there's another problem. Remember, without the aluminum, we had a transformation between 200 and 300 degrees C. And now this is shifted downward, so around 100 to 200. So aluminum additions do not really solve the problem. So what can we do? We came up with 2 ideas. One is heat treatment. We call this a recovery heat treatment. And the other one is further change in alloy composition to basically stabilize the microstructure. Okay, so let's start with the recovery heat treatment. You have seen this data before. So initial material fully martensitic, upon aging fully austenitic. And then if you do a short 5-minute heat treatment at 600 degrees C, and then you do the X-ray, you see all the martensite peaks, they reappear. So what you do here, basically you dissolve this detrimental omega phase, more or less fully, and you restore your initial microstructure. So then we apply this to cycling. So you see this first cycle. After this first cycle, you had a very short heat treatment, only 5 seconds, at 600 degrees C, which we call a reset cycle. Then we ran the next cycle, did the next heat treatment, and so on. And now you see that these cycles become stable. But you can cycle this on forever without a change in the hysteresis loop. Have we really solved the problem? I'm not so sure, because for an actual actuator, it might not be possible to shortly heat this up to 600 degrees C. And then there's, of course, the issue of structural fatigue. After these cycles, we looked at the surface of the sample, and this is an EVSD study here. What you see here is the orientation of the individual grains. And these tiny dark features in here are all cracks. And you see that the cracks have a tendency to show up in these green areas. So they do show up in the grains that have this 101 orientation. And up here, this is the theoretical transformation strain. You see the cracks form in those grains that have the large transformation strain. So the problem here is strain incompatibility. Some of the grains do transform, others do not, and then you get locally high stresses, and that's what's causing the cracks. I think there's a pretty obvious solution to this problem. One basically needs to strongly texture the material so that all the grains have more or less the same orientation, and then the problem is solved. In the next step, we did some combinatorial research. Actually, this was done by a colleague of mine, Professor Ludwig, at the University of Bochum. Here you see the tantalum content, and this here is 2 theta from an X-ray study. And then normal material has a composition of 30% tantalum. And here you see the martensite peaks. And interestingly, when he lowered the tantalum content, those martensite peaks were still present. So based on this work, we thought, okay, maybe low tantalum content materials do work as well. So we did cast some bulk materials. And actually that's what we got. This is here's the martensite star temperature. This is the tantalum content. This is the old data here that was available in the literature. This is from a study of Corcio. This is the material that we started to work with. And now this is the material with the very low tantalum content. And you see if you reduce the tantalum content, you shift up the martensite star temperature to above 400 degrees C. So this is a very interesting material. Problem, of course, is if you do the cycling, you see that again this material starts to degrade pretty rapidly. But then the solution is pretty obvious. Let's add aluminum. Let's see what's happening. You see this is between 400 and around 500 degrees C. And if you do add aluminum, here this is 5% aluminum, you see that the loops become much more stable and the temperature is shifted a bit to 300 to 400 degrees C, but this is much more than what we needed in the first place. So the stabilization works here as well. So if you compare this new material with what is on the market, here we have transformation temperatures. This is the reversible strain. Then the standard nickel titanium is around here. So you have high strain, but a low transformation temperature. Or you have these other materials that have very high transformation temperatures, but not much strain. And so far the only solution was nickel titanium with lots of noble elements. And with this new titanium tantalum, we were able to move from around here up to here. So we have pretty good temperature capability, and I would say decent strains. And if we induce the strong texturing, then we think we can move that direction. And then these materials might really make it. So to conclude my talk, I try to show you that the titanium tantalum material is really a promising high temperature shape memory alloy. It can work beyond 120 degrees C. We are not at 3% strain yet. We have calculated something like 2%, but I think we can manage that. It's reasonably priced, and it shows decent cyclic stability. And really interesting are those low tantalum alloys. We still have to look into structural fatigue, texture. That's something we can easily solve. But in this temperature range, oxidation might play a role. That's something we already look at. And we also try to model the material and predict its degradation behavior. And I hope one day these materials might make it to a real product. That's all for now. Thanks a lot. And I'm ready to take on any questions you might have.